I love archive.org. It's a great website. Yeah, so I'm starting again now. So let's talk about mazes for a second. I love archive.org. First off, just got tons of like software in there that you can actually play old arcade games or software that's classified as abandonware. And of course, some people don't respect copyright law and occasionally upload stuff they shouldn't there. You know, as I needed once an entire season of My Hero Academia, which I'm a big fan of. Great anime. That and Spy Family are some of my wife and I's favorite stuff to watch together. We have disparate choices, but we both like shonen. It's very good. Anyway, you may recognize this puzzle. It came from this book called the Maps and Mazes. It was a book I had as a kid, and I was happy to get another 2 copies actually. And you know, here you can see somebody drew in it for this labyrinth, and it's all nice and windy. Labyrinth is kind of a classic puzzle there. And the thing about labyrinths is that they're nice and windy, and they're hard for humans to solve like that. And this one, you know, it's got tunnels to go through to other places that just make it harder. But at the end of the day, maps and mazes and all these stuff are all graph problems. That makes, for computer science, it makes that really nice for these kind of things to solve, either being different states or different locations, different transitions. I mean, this one's like a classic graph problem almost a classic graph problem. I like it, where basically it's about a empire that's entirely based on an economy of goose trading, and the idea here is that, you know, the red flags mean you subtract 6 geese and 3 is to add, and you want to get to the castle. You know, what is the so basically it's a graph problem with nodes and edges, you know? And you know, so a lot of problems can be reduced to graphs, but probably none as classically as the maze. Now, if we were in America, I would suggest I would talk, especially if it was October, I'd talk about hedge mazes. I'm not sure if that's a thing in Japan or not, though. Do you know what I'm talking about by a hedge maze, or no? It's actually quite an interesting phenomena because of the amount of farmland that is available in the United States. Just again, the sheer amount of space in the United States does allow for kind of, you know, big things like this, where basically you can go in and it's either going to be made from that, or it can be made sometimes from corn. You know, I think I've seen it with corn. Yeah, corn maze out of cornfield. You know, so there's one, and you know, it's very, you know, kind of hard to figure out how to get through these things. But quote unquote, everybody knows, don't know who everybody is, but like everybody who's bothered like researching mazes and stuff like this knows that basically you need kind of 2 things to get through a maze. The first is string. And in fact, we see this in some of the classical art. Here is Theseus going to slay the Minotaur. I always forget if it's Perseus or Theseus. Honestly, it's always one of Zeus's children. All Greek mythology is that Zeus decided to commit infidelity, and now everybody else has to suffer for that. But anyway, but you can see there's Theseus. He's going to slay the Minotaur. He's in the labyrinth. It's a very classical tale. And you can see in his head, because the wonders of Google and their high-res scans, you can see what's grasped in his hands. It's Ariadne's thread, the thread given in by the princess. And here it is to wind back. This is analogous to a stack in terms of computer science structures. The ability to unwind, to push stuff onto the stack, and then to pop something from the stack is to rewind, to go back. Okay? This is obviously a very powerful structure here. And the other thing you need which he can replicate with his sword, is some way to make marks, right? Typically, this is done with chalk to basically color stuff. In our maze program, we accomplish this by coloring the wall, by coloring the various spaces in our maze. Okay, so those are the two things you need to basically solve a maze, to solve any maze, which is to have a way to go back to where you were and have a way to mark there. Now, what about solving mazes that change on you? That I think there's probably research papers written on that, but that's beyond the scope of this. But I guarantee you there are people who study that stuff. And the reason I bring this up is because in terms of like doing maze, in terms of like algorithm practice, mazes are like one of the very entertaining ways you can work at getting better at algorithms. First off, not just through maze rousing, figuring out the way through the maze again. We know how to do that. We know how to generate that. That's what this homework is. You're creating a way to get through a maze. But making a maze, there's a lot of more ways to make a maze, and they all have their own biases. For the extra credit, you'll want to use the depth first search implementation, iterative implementation, and it has a lot. It has a lot. Pop a cell from the stack and make it current, and then that's easy. If the cell has any current neighbors that have not been visited, choose one of those unvisited neighbors, and that makes it a bit difficult to actually generate the maze, which makes it interesting. Now, all maze generation things have biases. This maze was generated by an algorithm that has a horizontal bias, meaning that, long windy corridors left and right. The depth first search algorithm creates as a bias to making long mazes. Just these very long mazes. I'm personally enjoyed looking and seeing how this one works, which is the recursive division, where basically you recursively split. What you do is you basically take a space, split it into 4, add 3 doors, and then you recurse. You take a space, split it into 4, add 3 doors. And then you get yourself a maze, eventually, because it gets down to unit. And so there's this wonderful presentation that's linked on Wikipedia. If you actually look at these external links, sometimes they're actually really good. That's the other thing. Here's somebody talking about creating the best, and you can tell it's a good website because it's got no CSS in it whatsoever. It's just literally just HTML and links to pictures about how to do it. And this one talks about all the different ways. This is a great example of HTML kind of presentations you can do in this, talking about how these are graph problems, how it relates to graph, and it's got these animated things. Here's creating a maze using a drunken walk, or the drunkard's walk, because it basically it's saying we're just choosing. Basically what it's saying is that it randomly moves from point to point. Every time it hits a node that hasn't been visited, basically it opens up that space. So it's completely random, but it's very slow. Drunkard's walk is actually a thing. I'm sure if you've lived in Tokyo and been out late long enough, you've all witnessed what that looks like. But this one is a bit more efficient version of that, finding the end and going through, creating a binary tree. Sidewinder's pretty cool. There's all sorts of things, but again, there are variations to it. There's the recursive backtracker, recursive division. Oh yeah, and then of course, nifty is that you can make weave mazes. where, you know, you get paths that go above and over areas. I mean, again, mazes are fun, you know. They're challenging and interesting. In our and for the code that I gave you for the maze assignment, it's not too difficult. All you have to really do is follow the pseudocode, okay? And a lot of the answers are in the code I give you. Specifically over here, if we check out our data structures, because I know you're still probably working on your Josephus problem, and I'll be around to, or your solitaire, and I'll be around to help you with that in a second. But I wanted to make sure that you had the time that I mentioned this. Because why am I talking about stacks and queues? Well, stacks and queues are really just easy to use they're restricted linked lists. You can either only add to the beginning, or, you know, you can either only add and remove from the beginning of it, or you can add to the end and remove from the beginning. That's it. That's stacks and queues respectively. So in terms of like these files over here, right? You don't have to worry about maze too much unless you want to make it bigger. Maze grids panels where everything is. And this is one of those actually I'm kind of proud of, because I actually wrote it myself. You know, I didn't rely on anybody else having to. I wrote it from scratch, which is also why it's got some non-optimization. So basically, one thing to note is that every cell, right? Basically, it's a grid. So every cell is a thing in the grid, and by default, a cell has 4 walls around it. Every square has 4 walls, and then we generate the maze by removing the walls. The thing to keep in mind is that for ease of programming and me not having to think about it, your north wall corresponds to somebody else's south wall, right? So every cell, its north is somebody else's south, its east is somebody else's west. So whenever I was generating a maze, I did that by making sure I removed it. The maze algorithm I created was extremely easy. I just simply flipped a coin and said either remove your west wall or your north wall. Now, how do you keep track of where you are in the maze? First off, this is for each cell. You can change the background color of it by just doing set background and then saying color dot, and then you can give it one of the defined colors, or you can make your own color if you want. It's something you can do. And then visited, I've already made this function called visited, which given a row and column, it gets the cell that corresponds to that location, and then it checks if the color is something other than white or red. White being, you know, a normal space, and red being the finished space. And if it's been changed, then you've already been there. And then everything else can be done by following the pseudocode I provided for you. The other thing to help you I tried to make it so you don't have to worry about going out of bounds. That's the other big thing. And you can do that by checking for a north wall or south wall or east wall, because the way I have it is that, you know, you've got your window, and each of those sides of the window has a wall. So basically you can say, before asking, have I got, so what you want to do to ask if you can go somewhere is you ask, is there a wall in the way? And then you ask, have I been there? Now the reason you want to do that is because of short circuiting. Have you heard of this term before? Okay, so here's an example of one of the if statements we want to check. And that's my and symbol. Okay, if can go north 2, 2. So first off, what is north? So this is row column notation. So what is north in row column notation? If I'm at row column, what is this? What is the space in the grid above me? Row minus 1. Yep, that's north. Has been to row minus 1, same column. All right, so the idea here is that row minus 1 is, if I'm on row 0, row minus 1 would be negative 1, which in terms of arrays, that is an array out of bounds index, and that would cause an exception. However, if you do this like this, if I can go north, and there's a wall there, that means I can't go north. What short-circuiting is this idea that basically that if you've got an AND statement or an OR statement, if you've got a Boolean expression, if we can evaluate it early, then I will not check anything else. For instance, if I have something like, if I have basically something that goes false or true or false or false, dot, 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 right? If I've got this big Boolean statement of ORs, right? As soon as your compiler sees that OR, it's going to go, I don't need to check any of the rest. I'm optimized. I'm an optimized compiler. I'm not going to check anything else. Makes sense, right? Well, not your compiler, but, you know, the program. Okay? Now, the reason, and this, by the way, comes down to one of the questions you've maybe been having, or may not known you had. Why in the world am I using 2 bars? F, F, T, F, because that is what allows short-circuiting. If you didn't want to do short-circuiting, you would just use 1 bar. And that means that regardless of this being true or not, you want to run this one. That's because sometimes programmers are bad and they might do plus operations. And you should never do plus operations in if statements. But that's why. So similarly, if you had 1 AND, that means no short-circuiting. It also gets used as the binary operator besides the logical operator, but that's why you use 2 ANDs, because it enables that short-circuiting. You never really thought about it because it's just kind of the logic you follow as a human being. Anyway, as a result, basically, if you can't go north, you're not going to bother checking that space. Okay, so that is the main thing to be aware of. So long story short, you shouldn't have to worry about like being in row 0 or anything else if you frame your logic in the order that I've presented it. Okay, so now I will go around and help everybody.